Hi everyone, this is another the second video of the spacetime diagram series, and today I'm going to be discussing the world line of a photon, possible and impossible world lines, as well as the axes of moving reference frames. Okay, so let's first plot the world line of a photon. This is our origin, and the origin is the time and the x-coordinate where we first emit our light, and let's say that's 0, 0. So after 1 year, over here, after 1 year of light traveling, how far is it from our origin? It's gonna be 1 light year away. Oh, sorry. It's gonna be right over here. What about after 2 years? How far is it gonna be away? It's gonna be 2 light years away, and so on and so forth. So if you just keep plotting, then you're gonna get, okay, the line is pretty far off, but you know what I'm talking about. This is gonna be the world line of a photon. And let's call this angle theta. How do we work out theta? We can do it by using this formula, which is also in your formula booklet. V, velocity of an object over speed of light. The velocity of light is, c. So c over c equals 1, which equals tan theta. And arc tan theta equals, arc tan 1 equals theta. So theta is 45 degrees, and that's why this theta is 45. But if you are into trigonometry, you can easily realize that theta could also be 225 degrees. So does that mean a world line of a photon like this is possible? Let me just draw in a different color. This green world line is possible? Actually, yes, it is possible. But this is also a world line of light. But the only thing different about this black world line and this green world line is that the black world line shows a photon being emitted from the origin. It's being emitted away from the origin, from the 0, 0. But this world line of light, the green world line of light, shows the world line of light that is being emitted towards the origin. So in this video, I'm not really going to be discussing this theta equals 225 world line of light. I'm mainly going to be discussing the theta equals 45, but it's very useful to keep in mind there are multiple different world lines of light when you're solving some questions. That's going to come up later. Maybe I'll explain that later too in some other later video. Okay, so let's now first talk about possible and impossible world lines. So from our first few rules of relativity, we know that there's nothing faster than light. So let me ask you a question. Is this world line possible? The answer is no, because this world line shows that the object that's moving is faster than the speed of light, which is impossible. Now this is a little confusing because if I draw a kinematics diagram, which for a long time I said is very similar to a space-time diagram, except the axes are flipped, right? Displacement, time. Kinematics. In kinematics, we're used to seeing a less steep, a shallow graph and thinking, oh, that's slow. And a steep graph and thinking, oh, that's fast. But like I said, in space-time diagrams, the axes are flipped. So a steeper gradient means it's slower, and a shallower gradient actually means it's faster. So on that note, is this world line possible? Yes, it is possible because the line is steeper, therefore the line is steeper than the world line of light, and therefore this object is slower than light. So from that, we know that any world line that is within this shaded area is possible. But outside, which is the one I'm shading green right now, outside the red area, aka the green area, it's impossible. That world line is impossible. Okay, now let's try to plot a world line for a very fast moving rocket. So we got a rocket. I'm gonna draw it in red. Rocket. And we have an observer inside. Let's call him Alex. Alex is moving at very fast relativistic speeds, very close to light, but still slower than light. And if we were to plot the rocket's world line, it would look something like this, right? Rocket's world line. So if we have a world line for this kind of relativistic object, that means we have a moving reference frame, which in this case it will be denoted by S prime, and we're going to call this a moving rocket reference frame. So if we have a new reference frame, we want to plot another axis, the primed axis, then a new spacetime axis for this moving reference frame, because this very standard looking spacetime diagram with the perpendicular axes we plotted was for a stationary frame. For example, the Earth's frame, when we're talking about the stationary frame being the Earth and the moving reference frame being the rocket with Alex in it. Okay, so now we really want to turn this world line into an axis, a primed axis for the moving reference frame. But how do we do this? In order to do this, let's first understand the axes. Let's try to really understand the axes of our stationary reference frames. Let's first look at the x-axis here. So we have the x-axis, and no matter where we plot an event, as long as it's on this x-axis right here, the time of this event is always going to be 0, right? And we know this from our math classes. Therefore, here time is always equal to 0. Applying that same logic on the CT axis, no matter where we put a dot, no matter what event it is, even if it's super far away from the origin, as long as the event is on the CT axis, that means its x coordinate is going to be 0. That makes sense. I think that makes sense. And so applying the same logic, so now we're going to apply the same logic into the world line. All right, let me just clarify. So within this world line right here, from our Earth, from our perspective as observers, stationary observers on Earth, we see that as time passes, Alex's rocket moves. Specifically, it moves farther and farther away from us at a constant velocity. But what about from Alex's point of view? As time passes on, does he notice any difference in his x-coordinates? No, because whether time is equal to 0 or time is like 5,000, he's always just sitting his ass on his little dinky chair in a rocket. So he's always stationary. His x-coordinate is the same as when he started. It's forever going to be the same because, he just doesn't want to get up. And therefore, all throughout on this world line right here, Alex's x-coordinate, from Alex's perspective, moving the x-coordinate of Alex from a moving frame's perspective, x prime, I'll just write that in black. X prime is equal to 0. Basically, from Alex's perspective, the rocket is always in the same place. Just like how we think the Earth is always in the same place, although we know the Earth is always rotating and it's revolving around the sun, covering millions and millions of kilometers. So on this world line, x prime is always equal to 0. And this implies that this is the CT prime axis. You see the parallels? Okay, then how do I find the x prime axis? I wish I had a better explanation for this, but fortunately not yet. It has something to do with light having to be the same speed, same velocity in all reference frame. But basically, to get the x prime axis, you have to just reflect the CT primed axis across the world line of a photon. So it's gonna look something like this. And again, this is the x prime axis, and in this axis, CT prime will always be 0. And let's say if this is 20 degrees, this is also 20 degrees. And there you have it. We have the axes of a moving reference frame. I hope that was clear.